here we call chapter 4b. In fact, this is a continuation of the content of chapter 4 in our textbook. And majorly, the content is like I covered. First, the superposition theorem, and second is the Beveridge theorem. The third is Norton theorem, and the fourth, source transformation, and last one is maximum power transfer theorem. Okay, and these two theorems, okay, are also very, very important as far as the teaching goal of this course is concerned. 我们这门课来讲，这个非常 powerful 这个比较没有那么有名因为戴维里this French name 这个法国人的名字所以这 H 不发音Beveridge theory. Okay. So first, let's consider what is a superposition theorem. Okay, basically, this is a mathematical theorem, and which is valid for any linear system. In case you learn linear system theory, then this is a very fundamental theorem. Okay. And you can see the superposition theorem can be decomposed into two parts. The first part must satisfy the additive property. Okay. In case we have a function fx, and okay, if fx1 equal to y1, okay, this x1 belongs to the domain, and here y1 belongs to the range. Okay, then fx2 equal to y2, then we have this result. x1 plus x2 mapping to y1 plus y2. This is called additive property. Another property is called homogeneous property. In case alpha is a real number, okay, and also fx equal to y, then we have f alpha x equal to alpha y. In other words, alpha can be taken outside here. Okay. So sometimes you can combine these two properties by writing if fx1 equal to y1, fx2 equal to y2, then fx1 plus alpha x2 equal to y1 plus alpha y2. So this is the content of the superposition theory. Okay, and although the additive property here is only for two components, okay, in fact it can extend to n components. Okay, so here is an example of how do we use the superposition theorem to find to solve this circuit problem. Okay, we have input. Here is current source, 15 ampere, and we want to find the output current IO here. And we know all those components, they are all linear resistors. So this circuit system is in fact is a linear system. So we can use that property. Okay. So how do we solve this problem by using the superposition theorem? We can assume first IO is equal to 1 ampere, and we calculate the voltage drop and current, backward toward the input side. Okay, so if IO equal to 1 ampere, then the voltage across 5 ohm resistor is 5 volt. Okay, and the voltage V1 from here to ground, okay, is 1 ampere times 8 ohm, so we get 8 volt. And once we know V1 voltage, we know the current through the 4 ohm resistor. 8 volt divided by 4 ohm, we get 2 ampere. Okay, And from KCL, we know the current through 2 ohm resistor is 1 ampere plus 2 ampere, or 3 ampere. So we know 2 ampere here, then we can calculate the voltage drop across the 2 ohm resistor. Okay, so 3 ampere times 2, we get 6 volt plus V1. Okay, V1 we know is 8 volt, so we get 14 volt. So V2 now is 14 volt, and now we can find the current I3. Okay, so 14 volt divided by 7 ohm, we get 2 ampere. Okay, so here is 2 ampere plus I2, 3 ampere, we get 5 ampere. The source here is 5 ampere. Okay, so if the input is 5 ampere, we get a 1 ampere output. Now, if the input is multiplied by 3, what will be the output? Multiply 3. Wow, wonderful. So this is the linearity property, okay? And this is yeah. Okay, I'm sorry. 刚刚我讲介绍是介绍这个线性系统的特性，是还没有 touch 到这个 superposition。superposition 是有很多 source 啊。Okay, here is the context of the theorem. Okay. For a linear circuit, okay, consists of n input. Say U1, U2 up to Un. Then the output Y can be calculated as the sum of its components. In fact, this superposition theorem is the consequence of the linearity property of the circuit. 事实上，这个重叠原理是这个系统是线性的关系才会有这样的定理可以用这是因果的关系这非线系统就不见得是正确有时候可以对，有时候不见得对So you can see to calculate the total response, okay, you can calculate the component due to each source and add together. Okay, it's in fact something like additive properties of the linear system. Okay. So you can see here each output is due to only one input. Okay. So I think we can consider the example like this. Here we use another equation to explain this theorem. Okay. Suppose given a linear circuit and we have n current sources and assume this is a basic case. Okay. Those are all independent current sources. They are acted simultaneously, and this is another equation here. We can call this column GK1, GK. Okay, this is G1 column, G2 column, up to Gn column. Okay, so to prove this, first we have to review the so-called Crane's rule for solvent and linear systems. And here for dimension n equal to 3, given a square matrix which is non-singular, in other words, determinant of this A matrix is not equal to 0. By using the Crane's rule, we can write down the answer x1, x2, and this should be x3. Okay. The solution directed in terms of the determinant. So the denominator, okay, is the determinant of the A matrix. And for x1, you can replace the first column, of A matrix with this given vector. And similarly for the x2, x3, like this. Okay, so this is a Krebs rule. So are there any question? 你们都听过这 Krebs rule 这个用行列式来解线性方程式吧？因为我们后面都要证明一些戴维宁的定理，都要用到这个公式这样啊 ，2 by 2 matrix or 4 by 4 n by n matrix， 都是同样的一个形式啊，所以我们用3by 3的 case 做一个简单的双联啊。So you can see, given the knowledge equation here, and we have n current source active simultaneously. Okay, then we can find the node voltage, the case node voltage, by using the Krebs rule here, and the determinant of the conduction matrix is delta. And for this matrix here, we can expand the determinant. Okay, say if this is I1s, I2s, INs, then we can expand the determinant in terms of the last column. Okay, and I1s times the cofactor of I1 is this component. Okay, which is n minus 1 by n minus 1 matrix. Okay, it's determined together with this sign, plus sign or minus sign. It's called cofactor. So we can expand this determinant along this column. Okay, so we get this sum, okay, from j equal 1 to n. So you can see the node voltage, the case node voltage, in fact, is equal to sum of those components. Each component is like this. For example, EK1 component is due to I1s only, with all other current source equal to 0. Okay, so each time you need to consider only one current source, and especially in your electronics course, okay, some simple transistor circuit. When you replace the model of the transistor, the result circuit, although complicated, however, when you use this superposition, each time you consider only one source with all other sources equal to 0, then the complex circuit will be simplified. 所以在电子学里面，这个定理就很有用啊。你一个电晶体电路，一个放大器，看起来好像很复杂啊。那你一次只考虑 voltage source， 一次只考虑 current source， 其他都等于0的话，它有些被 short circuit， 有些被 open circuit。You can find the answer each component. You can find each component simply by inspection. 你就一些串变理，有些观察法就可以得出来。所以这个电理呢，是帮助你在电子学的课程里面的。我们电路学动不动都是非常复杂的电路啊，但是很少这样用。Okay, so here is an example. We have 3 current sources. Okay, this is a basic case. Okay, so the node equation is something like this. Okay, here's a conduction matrix, and the node voltage E1, E2, E3 are unknown. Okay, so in case you want to find the second node voltage E2 here, each time you can consider only one source. The E2 equal to, due to this current source only, with I2, I3 equal to 0. See, from the node equation we can decompose it into 3 parts. This part is due to I1s, this part due to I2s, and this part is due to I3s. Okay. So you can see here is the second node voltage due to I1s only. Okay. So the resultant node equation like this. Of course, this E1 1, E2 1, E3 1. It's just due to this current source only. And then you can calculate, okay, this. The second component, okay, is due to I2s, called E22. The first subscript means the second node voltage. So we have to let other 2 current source equal to 0. Okay, you can calculate this. And similarly, the third component here, okay, due to I3S only, we get these two closed source equal to 0. For this example, it seems the computational cost, okay, still, I mean, we don't save too much time by doing this way. However, in your electronic course, okay, normally you can find the component by inspection. 最主要在电子学的应用，我们在这一题里面呢是没有说节省多少时间因为这个电路还是要解330的这个 matrix equation， 那解3次其实反而浪费时间不过这是一个定理也了解对有些系统分析、设计、模拟各方面还是有帮助的。